So, we all know VSEPR theory is great for predicting the shapes of molecules, right? But it kind of leaves us with a huge question. How? How do atoms, with their rigidly defined orbitals, actually twist themselves into those shapes? Well, that's what we're tackling today. We're diving into orbital hybridization to finally bridge that gap.
Okay, so here's our game plan. We're going to start with a really interesting contradiction that VSEPR theory can't solve on its own. Then, we'll get the fundamentals down with sigma and pi bonds. After that, we'll unveil hybridization as the elegant solution, check out the essential hybrid toolkit, and wrap it all up with a foolproof guide to predicting any molecule's geometry. Let's get into it.
You know, VSEPR theory is amazing. Its whole idea of minimizing electron repulsion to predict shapes works like a charm. But again, it only tells us the what, not the how. How do the atom's native orbitals actually rearrange themselves to make these specific geometries? That's the puzzle we're here to solve.
I mean, really think about this for a second. A carbon atom's p orbitals are naturally oriented at 90 degrees to each other. So how on earth does it manage to form 4 absolutely identical bonds, perfectly arranged in a tetrahedron at 109.5 degrees? The math just doesn't add up if you only use its original atomic orbitals. It's this exact problem that forced chemists to come up with hybridization theory in the first place.
Okay, before we can solve that puzzle, we need to make sure we're all on the same page about the building blocks of these covalent bonds. Because, you see, not all bonds are created equal. They really come in 2 main flavors, sigma and pi.
First up, we have the sigma bond. This is the big one. It's the strongest type of covalent bond, and it's formed by the direct head-on overlap of orbitals. Just picture a straight line connecting 2 atoms. Now, this part is absolutely crucial. Every single covalent bond, whether it's a single, double, or even a triple bond, has one and only one sigma bond. It's the foundation.
So, what about those double and triple bonds? Well, after that foundational sigma bond is in place, any extra bonds are what we call pi bonds. As you can see here, they form from a side-by-side overlap of p orbitals that are parallel to each other. This creates these clouds of electron density above and below the main bond axis. And it's this setup that locks the atoms into place and stops them from rotating.
And this brings us to the solution, hybridization. It's this brilliant quantum mechanical model where an atom's own valence orbitals are mathematically mixed together. They're blended to create a brand new set of hybrid orbitals that all have the exact same energy and are perfectly shaped and pointed in the right direction for the best possible bonding. So you might be asking, why would an atom go through all this trouble? Well, it all comes down to energy. It actually takes a little bit of energy to promote and mix the orbitals, but think of it as a small investment for a massive payoff. The hybrid orbitals that result allow for way better overlap, which means they form much stronger and more stable sigma bonds. Nature always leans towards the lowest possible energy state, and hybridization is the way to get there.
Now, this whole theory is built on a few simple, really powerful rules. First, only the orbitals of the central atom are the ones doing the mixing. Second, the number of orbitals you put into the blender is the number of hybrid orbitals you get out. So if you mix 1 s and 3 p orbitals, you get 4 brand new hybrid orbitals. Third, these new orbitals are all identical twins, same shape, same energy, and finally, they will naturally spread out in space to match the exact geometries that VSEPR theory predicts. It's perfect.
Okay, let's open up our toolkit and see how this actually works. We can now describe these specific hybridization schemes that line up perfectly with the molecular geometries we see all the time. Think of these as the main tools an atom has in its belt to build molecules.
Let's start with the simplest recipe. If we take 1 s orbital and mix it with just 1 p orbital, we create 2 new orbitals. We call these sp hybrid orbitals. The other 2 p orbitals? They're left alone, unhybridized, ready and waiting to form pi bonds if needed.
And these 2 span orbitals want to get as far away from each other as possible, so they point in opposite directions. The result? A perfectly linear geometry with a 180-degree angle. This is exactly what you find in molecules like acetylene with its carbon-carbon triple bond, or in hydrogen cyanide.
But what if an atom needs to bond to 3 things? No problem at all. The atom just changes the recipe. It mixes its 1 s orbital with 2 of its p orbitals. This gives us 3 identical sp² hybrid orbitals and leaves just 1 p orbital untouched. These three sp² orbitals arrange themselves into a flat trigonal planar geometry with bond angles of about 120 degrees. This is huge. It perfectly explains the structure of molecules with double bonds, like formaldehyde or ethylene, and it's an absolute cornerstone of organic chemistry. You'll see this one everywhere.
So what about those atoms that love to break the octet rule? Well, for elements in the third period and below, they have an extra tool they can use. They're d orbitals. By mixing one s, 3p, and one d orbital together, they can create a set of 5 sp³d hybrid orbitals.
These 5 orbitals give us what's called a trigonal bipyramidal electron geometry. Now, check out sulfur tetrafluoride. The sulfur atom has 5 electron domains, but notice that one of them is a lone pair. And lone pairs are greedy. They take up more space. So that lone pair pushes the bonding pairs away, squishing the molecule into its characteristic seesaw shape.
All right, we've got the theory down. Now for the most important part. How do you actually apply this? Let's walk through a clear, repeatable process that will let you figure out the hybridization of any central atom every single time.
It's really just a simple 4-step process. First, you have to draw the correct Lewis structure. That's non-negotiable. Second, count up the total number of electron domains around that central atom. And remember, a domain is any single bond, double bond, triple bond, or lone pair. Third, use that number to figure out the electron geometry from VSEPR. And finally, you just match that geometry to its one and only corresponding hybridization scheme.
Let's put this into practice. For the carbonate ion, CO₃², the Lewis structure shows 3 electron domains around the central carbon. What does 3 domains mean? A trigonal planar electron geometry. And which hybridization gives you that? sp². Simple. Now for sulfur tetrafluoride, SF4, we count 5 electron domains around the sulfur. 5 domains means a trigonal bipyramidal geometry, which absolutely requires sp³d hybridization. See, it's a system.
And what's really cool is that this process works perfectly even for bigger, more complex molecules. In ethylene, for example, each carbon is bonded to 3 other things, so each carbon is sp² hybridized. This is what gives the whole molecule its flat, planar shape. In acetylene, each carbon is only bonded to 2 other things, so each one is sp hybridized, making the entire molecule a straight line.
Okay, let's pull all of this together into one clear summary, a kind of flowchart that you can use to tackle any hybridization problem that comes your way. This really is your key to success.
Here it is, your quick reference guide. Just look at the direct link in this table. The number of electron domains dictates the geometry, and the geometry, in turn, dictates the hybridization. It's a straight line. 2 domains will always be sp. 3 domains will always be sp². 4 will be sp3, and so on. This table is your best friend for any hybridization problem.
And here's the entire process laid out one last time. Draw the structure, count the domains, find the geometry, and assign the hybridization. If you follow these 4 steps, you can confidently and accurately figure out the hybridization and the local geometry for pretty much any central atom you will ever encounter.
So we've built this entire framework from the ground up, starting with a puzzle in VSEPR theory and ending with this elegant solution. The most important thing now is for you to apply this knowledge. So here's your challenge. Can you take this method and use it to figure out the hybridization in these new examples? Give it a shot.